My name is Adrián Mosquera. I'm hematology MD and PhD at University Hospital of Santiago de Compostela in Spain, and I'm also leading the computational genomics and hematology group, Greco in this institution. So we are mostly devoted to the development of AI-driven solutions for hematological cancer diagnosis and treatment. The question is very interesting. We do have a need to improve risk stratification in chronic myeloid malignancies before allogeneic stem cell transplantation, and particularly for myelofibrosis, because of the huge toxicity that is associated with transplantation. We know there are a percentage of patients who perform really poorly after 1 year of transplantation. However, despite this poor performance, the majority of patients do get a great benefit, even curing the disease. Actually, allogeneic stem cell transplantation is the only potentially curative therapy that we have available for this disease. So the point here was, it's key to better risk stratify these patients before allogeneic stem cell transplantations in order to better decide which profiles of which type of patient is candidate for other medical therapies that we have available now, with more targeted therapies being approved for myelofibrosis. So the point was, can we use machine learning techniques in order to enhance the identification of these patients? And for that, we did a collaborative project within the EBMT, and we collected data from more than 5,000 patients who underwent allogeneic stem cell transplantation for myelofibrosis in Europe. And these patients had all baseline data available before allogeneic stem cell transplantation. So we could cross this baseline data with their outcomes in order to identify risk. So for that part, we developed an approach in which we use different machine learning tools, such as random forests or deep learning tools, in order to predict risk, and also compare that with traditional Cox regression tools, and also with the previously defined CIBMTR risk stratification methodology developed by the Americans in order to risk stratify myelofibrosis. We train our models in a randomly selected group of patients, 75% of the whole cohort, and then use the other 25% of patients for validation. And we discovered that the random forest survival model was the best tool, which is actually not unexpected, because this kind of decision tree based models work very well for tabular data. And what we observe is that the model actually performs better, slightly better than the Cox regression model. That's not really a big achievement, but it's more generalizable when you take the same model to unseen patients to the test set. So the model actually behaves better, more generalizable than the Cox regression model and the other machine learning tools. And furthermore, we did also identify high-risk patients with this methodology. So most of the traditional Cox regression-based scores are thumb-based. So the statisticians first do Cox regression, identify variables and the magnitude of association of these variables with outcomes, and then generate thumb-based scores. And they say, okay, if you have 2 or 3 points, you are high risk. If you are if you don't have any or 1, it's low risk, and in the middle, it's intermediate risk or so. This kind of approach fails miserably in many situations, and in fact, the CIBMTR score that had been previously published only identified 8% of patients as high risk. However, we did identify roughly 25 to 30% of patients who do perform very poorly with this strategy, because we had this quantitative score, and we used some techniques to try to find the optimal cut point that could identify patients who do perform very poorly. And our high-risk group which is almost 3 times as big as the CIBMTR score group, does perform very poorly with overall survival, mortality, 1-year mortality of 40% and 2-year mortality well ahead of 50%. So this is really concerning, and it could drive some therapeutic shift in a few patients, or at least take a more informed decision in order to proceed to allogeneic stem cell transplantation in such a condition. When we did this research, the idea was, okay, let's try to test machine learning against traditional models and try to see if we obtain any different results that could be clinically actionable. But when we ended the study and we had this very important information to share with other clinicians, we faced the following difficulty. Contrary to thumb-based scores where you can actually calculate them very easily with your thumbs, with your hand, the machine learning models need a structure, computational structure to be implemented, and therefore we had to develop our own calculator and load that into the EBMT web page. So what we did is, with the final pre-trained model, we loaded that into a web page, which is fully interactive. Users can upload the 10 parameters for each patient. The model is based on 10 parameters, and these 10 parameters can be filled in the boxes, run the model, and the output will be a prediction of risk. In particular, we are dividing patients into low, intermediate, and high-risk patients. So the clinically actionable information is whether your patient is high risk or not. We also provide some survival risk bar, actually. So the higher the risk, the worse the expected performance of that patient with allogeneic stem cell transplantation. And we also added some notches in the bars to indicate some percentage of risk where outcomes are actually dismal. For example, we know that over the 30% higher group, a high-risk group, does perform poorly. They have overall survival of 50% at 2 years. So we added that as a notch to enhance the interpretation of the results that the web-based calculator provides to clinicians. And we also added another notch for the 7% higher risk score, because these patients who have an overall survival below 50% in the first year. I think it's very interesting for a large society like the EBMT to start working on artificial intelligence for supporting clinical decision-making in the field of cellular therapy, and particularly allogeneic stem cell transplantation. It seems like a paradigm shift. More projects are coming on the road, and I think if we follow the AAA of machine learning in medicine, which I have personally coined, which is broadly available, readily applicable, and clinically actionable, I think we'll deliver tools that are not just academically interesting, but clinically important to enhance our decision-making through data-driven approaches.